Good afternoon, everyone. It's very good to see so many of you have tuned in today to listen to what is going to be the first of 3 webinars from the physics department at Swansea University. My name is Simon Hands. I'm a professor here, and I'm going to be talking to you today about an aspect of something called special relativity. It's the theory of time and motion that we need to use whenever things are moving at an appreciable fraction of the speed of light. But before we begin the talk, I just want to say a few things. First of all, there will be some follow-up webinars on tomorrow and on Thursday at the same time. Tomorrow, we're going to be hearing from Professor Prem Kumar. He's going to be talking about black holes and space-time. So some of the ideas that he'll be using are also to do with relativity, a form of relativity called general relativity. So it's kind of, it's going to follow on from what we're talking about today, but will be more advanced. And then on Thursday, Professor Niels Madsen will be telling you about some of the things that happen at the particle physics laboratory called CERN, based in Geneva, including the experiments done by the Swansea team on antimatter. So that should be very exciting. And Niels is here today. I don't know if you can see him. He's represented by a small Lego man in the corner. Okay, so the talk that we're going to have today is actually being pre-recorded. I'm going to share my screen in a minute and play the talk. It runs for about 3/4 of an hour. During the talk, you will be able to ask questions. You won't be able to use the chat box, which some of you may be used to if you've used Zoom or Teams before, but there is a special Q&A box. You should see a button at the bottom of your screen, and you can ask questions. It's important to stress you can ask questions anonymously. You don't have to use your name if you don't wish, and I can quite understand it if you didn't feel confident enough to put your name to something. How we're going to do it is I'm not going to attempt to answer questions during the talk. Instead, actually, I'll be furiously looking things up, and then we will answer some of the best of the questions at the end. So there'll be a plenary session where we'll be all back together again. I'd also at this point like to introduce James Bateman, who you can see on the screen. James is our undergraduate admissions officer in physics. And he and I will be happy to answer any questions, not just about relativity, but also about any aspect of university life that you might want to know about. And I think that's all there is to say. Just to remind you, I'm going to play a pre-recorded lecture. That's not going to be as dire as it sounds because it was actually recorded live in one take. And to keep you on your toes, there is a deliberate mistake. So please watch out, and perhaps on the Q&A, if you'd like to say where you think I've made a mistake, that would be really interesting to see. So without any further ado, I'm going to start the process. I'm going to start the talk. So in order to do that, I'm going to share my screen. In this talk, I'm going to introduce the theory of relativity. That's the theory that we need when things are moving at an appreciable fraction of the speed of light. When we first encounter relativity, it's a theory of measurement, the way we measure times and the way we measure distances and how those are related to each other in an interesting and unexpected way. One of the most powerful things about the theory of relativity, however, is that it also impinges on the way we think about matter and energy. And the whole thing, as you're probably well aware, was originally devised by a famous physicist called Albert Einstein in the early years of the 20th century. So we're not going to cover the whole theory today. We're going to cover one of its more startling predictions. It's something called the twin paradox. And the reason I'm focusing on that is because it's fairly easy to demonstrate. The mathematics involved isn't too difficult. And the origin of the twin paradox actually goes, is very firmly rooted into what we know about light, the phenomenon of light. And I'm going to start by reviewing for you some facts about light, which I hope you're already familiar with. We're then going to cover something called the Doppler effect, which is what happens to light, what it looks like when the light source, the thing emitting the light, is actually moving, either moving towards you or away from you. And once we've thought about that for a while, I'm going to then set out the what are called the postulates, the basic ideas underlying the theory of relativity. I'm going to show you, or try to persuade you, that they're very firmly rooted in observations and experiments which have been done. And once we've set all that up, then we can go ahead and introduce our twins, who in this lecture are going to be called Alice and Bob. And we're going to review some of their adventures and show you the very remarkable paradox that results when people move very fast. So without further ado, let me lay out for you 4 facts about light. The first fact is one we actually know from a very young age. Light travels in straight lines. And the evidence for this is startlingly easy. It's around us all on a sunny day. It's the existence of shadows. So the fact that light can't go around corners means that if something gets in the way of the light source, like the sun, then a shadow is cast which is relatively darker. So shadows are evidence for light traveling in straight lines, and in fact that's true so far as we know, as long as we're thinking about distance scales which are much greater than, say, typical wavelength of light, and we'll come on to that in a minute. The second fact that we're going to need about light is that it travels at a finite speed. And the reason this isn't obvious is because that speed is absolutely enormous. It's 3 × 10⁸ meters per second, or 300,000 kilometers per second. And we need to stress that that's way faster than any speed normally encountered or experienced by a person running or driving a car or flying a jet plane, or even traveling in a rocket. So that's one reason why relativity isn't very familiar to us. It's simply because most of the time we don't explore anything like those speeds. How do we know that light travels at a finite speed? Well, one reason is that we can look up into the sky and we can look at objects which, in effect, we can use as clocks. So one example would be if we look at the planet Jupiter. It's got 4 moons orbiting around it in a very regular and well understood way. However, Jupiter isn't always the same distance from the Earth, depending on where Jupiter is in its orbit around the Sun and where the Earth is in its orbit around the Sun. Sometimes it's further away. And in fact, when people observe the behavior of the moons, you can see that sometimes the clock is running a little bit more slowly than you might expect. So that when, say, one satellite gets to its furthest distance from Jupiter, it happens a little bit later than you might expect. And the most natural and simplest explanation for this is that the light from Jupiter and from its satellites is taking time to get from there to here. And that's because it can only travel as fast as 3 × 10⁸ meters per second. And of course, this is a commonplace observation now. We know from space missions, when we send probes to the outer parts of the solar system, in fact, we know that the signals that we send to control the probes, and that the signals that the probe sends back to us, maybe photographs or scientific observations, that can take, well, several hours if it's from way out in the furthest reaches of the solar system. So although light's speed is very, very fast compared to our common experience, actually the consequences of it being finite are well understood. The third fact about light is that it's a wave motion. And that means that it consists of waves, and we can characterize those waves by the distance between successive wave crests, and that's called the wavelength. It's usually denoted in physics by a Greek symbol lambda, and that's what I've written on the slide here. And because light is traveling with this enormous speed, those wave crests are passing us. And so we can also characterize the light by something called the frequency, which is the number of wave crests which pass us, or which enter our eye, say, in a second. And that number is called the frequency. And in fact, the relation between the two is that the longer the wavelength, the lower the frequency, or the shorter the wavelength, the higher the frequency. And in fact, if you multiply the frequency by the wavelength, it always comes out that the product of those two quantities is equal to the speed of light. So it's interesting to talk about frequency because it's responsible for one of the most obvious qualities which light has, and that is the color of the light you see. So it's a fact that light of different colors has different frequencies. One thing we're going to use in this talk is that red light has a lower frequency than blue light, and that's what is written there on the slide. So I hope that actually most of these things you already knew, but these are the things we're going to use to develop our ideas and ultimately will lead to the theory of relativity. So one way in which these ideas relate to each other and kind of lead to something interesting is when the things which are emitting the light are in motion. Because when light is emitted from a moving source, that can actually lead to its frequency with which the light is observed being shifted. There's a name for this, it's called the Doppler effect. And one place that we can actually observe the Doppler effect is if in the night sky, many stars we observe are actually part of what are called binary systems. That means they're actually two stars, and they may be orbiting around each other, much like the planets orbit around the sun. And that means that at any given time, one of the stars may be moving towards us, and the other star will be moving away from us. Now, when the star is moving towards us, the light which it emits looks a little bit bluer than we might have expected. In other words, its frequency is larger than the frequency we might have expected to see. How do we know what color light to expect? Well, we know that because stars emit light in with characteristic frequencies related to the chemical composition of their atmospheres, and we can examine that by taking what's called a spectrum of the light. So actually we can measure this shift in frequency by comparing the spectrum of the starlight with the spectrum of a sample of gas or whatever chemical it is taken in a laboratory. So the Doppler effect says that the light from an object moving towards us is bluer than we expect. That's sometimes called a blue shift. By contrast, the light coming from the star which is moving away from us looks redder than we expect, and that is because its frequency is less than the reference frequency. Now, the interesting thing is about a binary system is that the stars are constantly orbiting around each other, so that the star which for now is moving towards us, a certain time later will be moving away from us, and at the same time the star which is now moving away from us will be moving towards us. So if you observe the spectra of these stars, you'll see a kind of a dance. The spectrum will be split into two, with one component slightly bluer than we expect and one component slightly redder than we expect, and those will move apart and then move towards each other and merge and then move apart again in a regular pattern, which we can relate to the orbit of the stars around each other in the sky. And what that means is that the light we observe from binary systems exhibits regular color variations. And that's a very interesting observation, and it actually helps us to work out the properties of the stars in question. So it's a very useful tool in astronomy and astrophysics. Okay, so now let's focus for a little while on Albert Einstein, the physicist who first developed the theory of relativity. Most of us know about Albert Einstein. We know that he's an old man with fuzzy grey hair and a very impressive moustache. He looks extremely wise, and he's become a bit of an icon. You'll find his photograph everywhere on the internet, on t-shirts, on tea towels, and he's got a lot of very wise sayings about the ways of the universe, which many physics enthusiasts like to quote. So this is perhaps our mental image of Albert Einstein, and it's actually very startling that when he developed the theory that we're talking about today, he looked a lot more like this. He was a young man. He was in fact 26. And I find a rather disturbing fact. He's much closer in age to you than he is to me. So it just goes. This just goes to show that our image of what physics, science, and what the people who do it is often doesn't really match the reality. Very often, very startling things are done by quite young people. Okay. Let's launch into the theory of special relativity, as originally set out in a very famous paper Albert Einstein wrote right at the beginning of the 20th century, 1905. It's based on what are called two postulates. The first postulate is that the velocity of light in a vacuum, that means when it's not going through a medium like air or glass, the velocity of light is constant. It doesn't depend on how fast the thing emitting the light, the source, is going. It doesn't depend on how fast the thing receiving the light or observing the light is going. Everyone who measures the speed of light will always get the same answer, that number we called c, 3 × 10⁸ meters per second. This is actually quite a surprising thing, and it appears to defy common sense, where we think of, if we think of light like a stream of bullets or missiles, you would think that if the star, say, that is moving towards you and emits bullets or missiles, they'll be going a little bit quicker because they'll have the speed of the star added on. Well, if that were true, it would have observable consequences. If we think about the binary star system again, if the blue shifted light was traveling faster than the red shifted light, it would get from the star to the Earth sooner. And therefore, this regular pattern of the two spectra, the point of maximum blue shift and the point of maximum red shift, they wouldn't be in sync. They'd be all over the place, and it would be much harder to disentangle what was going on. And there's no evidence from our observations of binary star systems that that's going on. It's much, the observations that have been made are all consistent with the fact that the red shifted light and the blue shifted light have got from the stars to the Earth in the same time. They've been moving in the same speed, and the only difference between the light from the stars is in the shift of their frequency. So that's the first postulate of special relativity. The second postulate, the laws of physics are the same in all inertial frames of reference. It's impossible to perform an experiment to detect absolute motion. What does that mean? First of all, I'd better say what an inertial frame of reference is. That means that you're in a frame of reference where you, the person at the center of things, are either at rest or you're moving in a straight line with uniform velocity. It means that you're not accelerating. And it's important to say at this point that the theory of relativity that we're outlining today is all to do with inertial frames of reference. We're not talking today about anything which is accelerating. That's a different and equally important, if not more important, story, but it's beyond the scope of what we're talking about today. And that's why sometimes the theory we're talking about today is called special relativity, because it applies to inertial frames. How might an absolute motion be defined? Well, one way in which it would be defined is if there were a medium which carried the light waves. It's not unreasonable, because the other signal, which is a wave, which we know about and are familiar with, is sound. Sound is a sequence of oscillations of alternating pressure, high pressure and low pressure, in air. And sound is therefore carried by a physical medium. We can feel air, we can measure it, we can compress it, we can measure its density. So when people first start to understand light in terms of a waveform, it was very natural to think that there would similarly be a medium which carried the light waves. And if something's natural to think about, it's natural to give it a name. The name that it was given is called the ether. Well, we know that sound is carried by a physical medium, and it can therefore, we can actually measure its properties. One way in which we know about the air is if we go outside on a windy day. If the air is in motion around us, we feel it. We feel it in our faces. We find it difficult to cycle against. In fact, we could even detect the wind and the speed and direction of the wind by doing careful experiments with sound, because the speed of the sound moving against the wind is slightly different from the speed of sound going downwind. So a characteristic of a medium is that it alters the speed of the light waves. Could we therefore detect an ether which carries light waves by measuring the effects of a wind? We know that the Earth is in orbit going around the sun and moving actually rather fast, perhaps 30 kilometers per second, something like that. So surely if the Earth is moving through the ether, then there'll be an ether wind, and we should be able to measure it by carefully measuring the speed of light along the direction of motion of the Earth and at right angles to the direction of the Earth. This was a very natural way to think at the turn of the 20th century, and in fact two scientists called Michelson and Morley performed they did better than think. They performed an experiment to see if this ether wind could be detected, because they worked out the size of its effect, and they built apparatus which was capable in principle of detecting the difference between the way light traveled along downwind and across the wind. And one of the remarkable things about that experiment is that it failed to detect any wind effect at all. And so the Michelson-Morley experiment is direct experimental verification for the second postulate. It's actually, they were trying to do something which was impossible, which was to detect an absolute frame of reference with which we can define absolute motion. And what this says is that, as it says in the postulate, the laws of physics are therefore the same whenever they're measured by anybody who's in an inertial frame of reference. Okay, so let's keep these postulates in mind. I'll try to point out to you when they come in, and we're going now to do an argument to show how they might lead to some interesting effects. In order to do that, we're going to consider a diagram of people in motion. I'm going to label the people as A and B because that's the easiest way to write labels with simple letters, but it doesn't hurt if you actually extend it and think of A as being an observer called Alice and B as an observer called Bob. So in order to talk about their motion, we need to talk about where they are, their distance from where they started, and also when they are, so the time that's elapsed. So therefore it's very natural to portray their motion on a two-dimensional graph where the distance across the horizontal axis measures distance, and the vertical axis measures time. So what's drawn here, this red arrow, is Alice's trajectory. What you can see is it's going straight up the graph. That means that her distance from the origin is the same at all values of the time. What that means in real words is that she's standing still. She's at rest. Her distance is not changing with time. And for a particle or a body or an observer at rest, the trajectory looks like a straight line going straight up the page. In contrast to that, this is Bob's trajectory. So at early times, at time 0, at the bottom of the diagram, Alice and Bob are at the same point, and their trajectories therefore cross. But then Bob's trajectory is a straight line moving at an angle. And as time increases, the distance between Bob and Alice is getting bigger and bigger. And it's getting bigger in a uniform way. If you think about a particular point on Bob's trajectory and you measure the distance as the x coordinate and the time as the y coordinate, then you can see that the slope of the line, the time t divided by x, is just 1 over Bob's velocity, v, because velocity is distance divided by time. So what this means is that a straight line at an angle to the vertical represents a moving object. If the line is straight, that means that the velocity is constant. It doesn't change in time. And that's what we expect of an observer who stays within an inertial frame. So the special theory of relativity is all about straight lines in this kind of space-time diagram. Okay. So we're in a situation where Alice and Bob were together at the beginning, and now Bob is moving away with constant speed to the right. Alice would like to do an experiment to measure how fast Bob is going. How can she do that? One way is that Alice can send a signal to Bob, and Bob can, when he receives the signal, can send another signal back to Alice. That signal I've represented as a black dotted line, and that's the most effective signal we can think of sending, is a light beam. So one way of visualizing this is to think that Alice is holding a torch and she shines it at Bob and presses the on switch, and a beam of light flies between Alice and Bob. Now, we know from what we learned earlier that the speed of light is finite. So therefore, the trajectory of the light beam is going to be a straight line at an angle. If you look, it's at a bigger angle to the vertical than Bob's trajectory, because the speed of light is very big compared to Bob's speed, or it's certainly larger. So therefore, just from the geometry of this diagram, we can see that the signal going from Alice to Bob will eventually intersect Bob, but at a slightly later time, because the light needs time to catch up with Bob. Similarly, when Bob gets the signal, he can take out his torch and shine it back towards Alice. And that beam will go at the same angle but in the opposite direction. And it will take some time to get back to Alice. So therefore there's a measurable delay between Alice sending out her light signal and receiving the return signal from Bob. She might also choose to repeat the experiment a little bit later on. It looks very similar, but all of the distances involved and the times involved are stretched slightly, because by now Bob's further away, so the light takes longer to get to him. Well, let's try to put some numbers on this. Let's suppose that Alice sends the signal to Bob after a time t after he initially left. What time does Bob get that signal? Well, that's what we want to work out. For now, we're going to call it k times t, where k is a number we're going to try to work out. But on general grounds, k is going to be bigger than 1. In other words, Bob's not going to get Alice's signal for a longer time than the time that Alice waited before sending it, simply because Alice's signal has to take time to travel all the way from where she is to where Bob receives it. So therefore, in general, kt will be larger than t. Now, think about this whole procedure from Bob's perspective. Bob is an inertial frame, so in his own frame of reference, he thinks he's standing still, and what he's seeing is Alice flying away from him with the same speed, but in the opposite direction. So if Bob waits kt before sending his signal and then sends it back to Alice, the time that Alice receives it will be a factor k times kt, or k squared times t, since the time when they were together. So that stretching factor, kt and k squared t, is the same in both directions, and that's really just a consequence of the special relativity postulates. First of all, that the speed of light is always the same, regardless of the speed of the observer or the speed of the source. And secondly, that it's really impossible to decide whether it's A at rest and B moving, or B at rest and A moving. They're both equally legitimate points of view. Okay. One way of understanding that the time between the light, that the interval that Bob receives the light is longer, has been stretched. It's actually an instance of the Doppler effect. Another way of saying this, therefore, is that the frequency with which Bob observes Alice's light signal is 1 over k times the frequency with which it was emitted from Alice's torch. That's nothing more than the effect that we talked about when we were discussing the binary stars. So our goal is going to be to calculate this Doppler effect factor k in terms of Bob's speed. I'll show you how this calculation goes. It's going to go a little bit quickly, so I would just listen for now. If you want, it will be of benefit to you perhaps to go through these steps again later with a pencil and paper, and you can always replay the slides to get the expressions correct. Okay. If Alice works out the time between sending her signal and receiving the return signal from Bob, it's k squared minus 1 times t. And it's very reasonable for Alice to deduce that the time that her signal got to Bob was exactly halfway through, because she knows that light travels the same going from her to Bob and from Bob to Alice. It's the same speed. So therefore, just by doing a little bit of geometry, she can work out that the distance that Bob was from her when her light beam got to him was basically how far light can travel in half the time of k squared minus 1t. And that gives the expression there, c times k squared minus 1 times t divided by 2. So she knows the distance. In order to work out Bob's speed, she also needs to know the time, and she can do that actually by just subtracting, using the fact that it was t to the moment that she emitted her first signal, and then it's a half k squared minus 1 times t receiving the return signal, and she can do a little bit of calculation and work out that the time at the moment that Bob received her signal was a half times k squared plus 1 times t. So now let's do the calculation. Bob's speed is the distance divided by the time. We argued that the distance was c times k squared minus 1 times t divided by 2, and that the time was k squared plus 1 t divided by 2. So if I divide one by the other and tidy it up a bit, I can work out that the Bob's speed in units of the speed of light is given by that expression, k squared minus 1 divided by k squared plus 1. And then it's possible to do a little bit of algebra. Again, you might want to do this in your own time to work out the Doppler shift factor k in terms of Bob's speed v. It's the square root of 1 plus v over c divided by 1 minus v over c. So we've used this rather geometrical approach of the space-time diagram to work out the effect by which light from a moving object, its frequency is changed, the Doppler shift which we discussed earlier in relation to the binary stars. There's a couple of things that I'd like to point out to you in this formula. One is that you can think of v either as b's speed away from a, in other words, if you assume a point of view in which a is at rest, but it's equally valid to think of it as a's speed away from b, in the point of view where b is at rest and a is moving away to the left. The same formula works, and that's really, again, a direct consequence of the special relativity postulates. The other thing to notice with this formula is it's got what's often called in physics a symmetry. If I take v and change it into minus v, if I change its sign, that's the same way as saying and change it into minus v, if I change its sign, that's the same way as saying that instead of the velocity being b moving away from a, that would be the description of b moving towards a. And if I change v to minus v, you stare at that formula, you should be able to convince yourself that it has the same effect as changing k to 1 over k. And that tells you that the same formula can describe both a redshift, where b is moving away from a and k is greater than 1, and it can also describe the case of a blue shift, where b is moving towards a and k is less than 1. And that's nice. It's nice when we have a formula which can do which can serve for two slightly different cases, the red shift and the blue shift. Well, we've done most of the maths now. I hope you didn't think it was too difficult. I'd now like to go back and discuss another little adventure that Bob and Alice could have. And this time Bob is going to stay at home, at rest, so therefore Bob's trajectory is a straight line going straight up the page. Alice goes on a journey, so she's with Bob at the beginning and then she flies away to the right, but at some point she stops. She turns around and travels back in the opposite direction at the same speed. And therefore, the trajectory in the second half of the motion is a straight line pointing not to the right but to the left, but it's at the same angle to the vertical. And therefore, at some point in the future, A and B, Alice and Bob, are together again. At the point where she reverses direction, at the furthest extent of travel, Alice chooses to send a light signal to Bob. It could be a simple flash of her torch. It could be something more involved, like, I'm on my way back, put the kettle on. And we can now try to use the same sort of arguments that we looked at earlier to try to work out how the time intervals go. This time, from Alice's perspective, the time that she flies away, the first leg of her journey, I'm going to call t. When she turns back, she's moving at the same speed and she has to cover the same distance but in the opposite direction. So the second leg of her journey is also going to take t. However, because Alice and Bob are flying apart from each other, we know that Bob is going to measure the time of that initial signal, telling him to put the kettle on, not t, but rather an extra factor k times t after their initial, after the start of the journey. That's a manifestation of redshift. K is larger than 1. On the way back, Alice thinks it takes t, and she is sending lots and lots of messages to Bob. And they're all flying at the same speed. And you might be able to tell from this diagram that actually, although Alice is sending the messages at fairly regular intervals, they're actually rather crowding up. And B is getting Alice's return signals fairly rapidly. And in fact, it's because now that Alice is traveling towards Bob, in effect, all her signals are being blue shifted. So therefore, when Alice takes a time t to get back, Bob measures that time as 1 over k times t. Eventually, Alice gets back to Bob, and they're in the same place at the same time. They can compare their clocks. They can just get them out of their pockets and put them next to each other, and they can compare the duration of the journey. And here's where the amazing thing happens. From Alice's perspective, she took a time t to fly out and she took a time t to fly back, so that the total time which elapsed between the two meetings is just 2 times t. For Bob's perspective, we have to add up kt, the time he measures until Alice gets as far out as she does, and then 1 over k times t, which is the time she takes to get back. Remember, we have a formula for k in terms of Alice's flight speed v. It's the Doppler shift factor. There's the formula. It's quite complicated. So now we can substitute in that expression for k into the formula for the time that b measures. I won't go through the math. It's not too difficult. And here's the answer. Bob's measurement of the time to the meetings is 2t divided by the square root of 1 minus v squared over c squared. Now v over c is always less than 1. So 1 minus v squared over c squared square rooted is a number which is less than 1. So therefore 2t is being divided by a number which is less than 1, and therefore it's going to be greater than 2t. And here's the amazing outcome. The time that Bob measures between their first meeting and their second meeting is greater than the time that Alice measures. They can put their clocks together. They might have synchronized them when Alice set off, but they'll be getting different readings when they get back. And that is the effect that's known as the twin paradox. That different observers, different voyagers who've had different experiences, not only have they gone different distances between first meeting and second meeting, but they've also experienced different time durations. And that's something which we're completely not used to in a world where we don't really travel very fast compared to the speed of light. But if we're talking about space journeys, that effect can actually be considerable. So let's think about a prospective journey where Alice wants to travel to a nearby bright star. The star she's chosen is called Sirius. There's a photograph of Sirius. And it's 9 light years away. That means that a beam of light leaving the Earth would take about 9 years to get to Sirius. Alice has the latest rocket ship. It's capable of traveling at 4/5 of the speed of light, or 0.8 times c. So she sets off from the perspective of B, who chooses to stay at Earth and sit at mission control. How long is Alice's trip going to take? Well, she's got to go 9 light years to get to Sirius. She's got to go another 9 light years to get back. And she's traveling at 8/10 of the speed of light. So the little calculation is laid out for you there. It'll be 22.5 years between Alice leaving and Alice returning. That's quite a long time, quite a significant commitment for Alice's mission in terms of, you know, a fraction of her potential lifetime. But what about Alice? How long does she think she takes? Well, she has to correct that factor by the factor which we just calculated. And on Alice's clock, she thinks the trip takes 22.5 years multiplied by the square root of 1 minus 0.8 all squared. And if you put that into a calculator, you'll find it's significantly less, 13.5 years. This is why it's called the twin paradox, because Alice and Bob could be twins. But when they return after Alice's mission to Sirius, Bob has aged by 9 years compared to Alice. This effect that time can somehow be stretched out or compressed for different observers moving at different speeds, it sounds like science fiction. After all, we still don't really, space travel to nearby stars still isn't really a reality for us, and there are enormous technical challenges to getting rocket ships traveling at 8/10 the speed of light. But time dilation does have consequences in our world. I'll mention one. It's very famous. There are unstable subatomic particles called muons. Muons are produced constantly in the upper layers of our atmosphere by collisions with very high energetic particles like protons coming from deep space. They're called cosmic rays. So muons are produced in our upper atmosphere, and many of them can be detected by detectors or observatories lower down at the ground. And actually that's quite a puzzle, because when we do experiments on muons in a laboratory when they're at rest, the muon's unstable. It actually tends to decay after only 2 microseconds. And the reason this all works is because the muons, when they travel from the upper atmosphere to ground, are actually traveling at 0.9997 times the speed of light, almost at the speed of light. And their effective lifetime in the Earth's frame of reference is therefore dilated. It's not 2 microseconds, it's 80 microseconds. And that gives the muons plenty of opportunity to reach the ground and to be detected as a muon at sea level before they decay. So time dilation has directly verifiable consequences, and it's real, as amazing as it sounds. Final thing I'd like to cover is, why do we call this a paradox? Well, if you're sitting with Alice on her rocket ship and you look at Bob, it looks to you like Bob is moving away from you at high speed, and then at some point he stops and then returns to you equally fast. So from that perspective, if you're on Alice's ship, aren't you the person who's been at rest, and isn't Bob the person who's had the interesting trip? Haven't you therefore had the same experiences but vice versa, the opposite way around, and shouldn't it be Alice who's aged more than Bob? Well, you might think that way, but it's not quite correct, because the experiences of Alice and Bob in this second experiment are not equivalent. The way we phrased it throughout the entire story, Bob remained in an inertial frame. He remained at rest in mission control on Earth. However, Alice, when she got to Sirius, at the very furthest extent of her trip, she had to reverse direction. In practice, that's a big deal. She would have had to have turned on the motors in her rocket ship in the opposite direction, which is going to decelerate, bring herself momentarily to rest, and then to accelerate back in the opposite direction towards Earth so that she could get back. So for that whole period when that was happening, she was accelerating, and the motors on her rocket ship were working extremely hard. So for a brief period, therefore, Alice was not in an inertial frame. She wasn't an inertial observer. And that means that Alice's experiences are not the same as Bob. And that is how we resolve this apparent paradox. There is no paradox because Bob is always an inertial observer, but Alice is not. Well, that covers, I think, one of the more startling consequences of the theory of special relativity, and I hope you didn't find the mathematics too daunting. As we saw, really, a lot of it could be done by just drawing large, clear diagrams and by also thinking clearly. And I hope you've found that enjoyable. Hello, everybody. I hope you can hear me. And after the talk, first of all, I want to congratulate everybody. If you were watching closely, many questions came in immediately after the deliberate mistake. And the deliberate mistake, if you didn't spot it, was that a microsecond is not 10 times 10 to the 9 seconds. It's actually 10 to the minus 6 seconds. And I spotted that the first time I watched the video for myself. It was a real dull moment. But since I don't know how to edit any of these things, we left it in. We did get some really interesting questions during the talk, and I would probably quite like to run through them. I think we've got some time. First question actually was a very practical one. Will the PowerPoint be available to us? It's not a PowerPoint. It was done using an Apple product called Keynote. But what the actual video of the lecture is available. It's a fixture on the Swansea University e-streaming site, along with another lecture that I've made, and we will be able to share the link with you. We'll find a way of doing that after, so you can go back and watch it carefully and pause it and work out all the sums if you need. I'm going to go through the questions as they came up during the talk because they're kind of thematically linked. A couple of people questioned very correctly my assertion that light always travels in straight lines, and pointed out that light can be bent by a gravitational field, giving rise to the effect known as gravitational lensing, and that this can happen sometimes in the presence of a black hole. And you're absolutely correct, those of you who pointed that out. So let me just explain that when we talk about gravitational effects, we're talking about not the theory of special relativity, but the theory of general relativity. And general relativity is, in some sense, it's a more all-encompassing theory than special relativity, because it applies not just to inertial frames, but to non-inertial frames. In fact, it turns out that general relativity is our modern theory of gravity. So I was quite careful during the talk to put in a disclaimer. We were strictly staying within the domain of special relativity today, and everything therefore was in an inertial frame, and in inertial frames, light does travel in straight lines. But it's a good way of flagging up tomorrow's talk by Prem Kumar, where he will be talking about non-inertial frames and general relativity and warped space-time and black holes. So if you want to pursue these things, tune in tomorrow. When we talked about the spectral lines from the binary star, someone asked a very quite tricky question here. How do we know which gas is causing the spectral lines if all the frequencies we see are actually shifted, either towards the red end or towards the blue end of the spectrum? And this is a general problem in astronomy. So the answer here is that you're probably aware, or maybe you're not. So every kind of atom emits a particular characteristic series of wavelengths. Sometimes it can emit wavelengths, so you see a bright spectral line, or sometimes it can absorb light from the surrounding medium, and then you see a dark spectral line. But each atom has a different pattern, but those patterns are very characteristic, and we can pick them out even when they've been shifted one way or the other. And we can turn that to our advantage, because we can use, by measuring it, we can say, aha, there is, I don't know, calcium in that star, but all the characteristic calcium wavelengths are a little bit longer than I was expecting. We can actually use that observation to tell us how fast the star is traveling away from us. In other words, we can measure the redshift of the spectral lines to calculate the star's velocity away from us. Along with that question, someone asked a really interesting question. I'm not quite sure where this came from. How do Fourier transforms apply to this, and what are they? Fourier transform is a mathematical operation which you normally wouldn't encounter until probably the second year of a physics or a maths degree. So I'm not going to go too far into it, but it's actually the mathematics behind taking a spectrum. So when we observe light, the light enters our eye, and the information we're getting is ordered in time. It's what's called a time sequence. However, when we take a spectrum, we're organizing the light or the information by frequency. And frequency, if you think about it carefully, is measured in units of 1/time. It's measured in frequency of hertz or per second. And the Fourier transform is the mathematical way of going from one way of thinking about the data, the time sequence, to the other way of thinking about the data, which is the frequency sequence. It's actually the same information, but just done in different ways. So Fourier transforms are very important in spectroscopy, but I don't think you'd thank me if I went further into the details of the Fourier transform right now. Okay. 2 or 3 of you actually questioned quite closely the change in direction which Alice made halfway through her trip. And I think you guys were getting quite close to the heart of the matter, which I did try and stress right in the last transparency. It's the fact that there was a period where Alice changed direction and had to accelerate. That actually costs money. She had to turn on her rocket motors. And for that brief period when she was accelerating, she was not in an inertial frame. So the fact that Alice and Bob have aged differently can actually be ascribed to the fact that Alice has spent time outside an inertial frame, whereas Bob hasn't. And then someone asked, when we were looking at the space-time diagram, when I was trying to be very careful, arguing about all the distances, t and kt and so on, shouldn't those arrows have been vertical? Shouldn't they have been straight up, because the time axis is vertical? And that's actually quite a clever question. Unfortunately, I'm not going to give you a complete answer, but basically the answer is no. It is correct to draw the arrows along the directions of the lines, because in the kind of space-time diagram I'm drawing, the length of the line on the paper isn't a direct measure of the duration of time. It's because time and space are measured in slightly different ways. And perhaps that's not as satisfying and complete an answer as you'd like, but it will have to do. What I was very careful not to do when making that presentation was actually say that line's 3 centimeters long and this line's 4 centimeters long. So the lengths of the lines in those diagrams were not actually a direct measure of the factor, the Doppler shift factor K. However, the arguments that I used to calculate K in terms of V, they were all based firmly on the postulates of special relativity. So the arguments, the logic I used is unimpeachable, but you can't actually check it with a ruler. And I think, apart from the people who were pointing out that I didn't know the distance to Sirius very accurately, the many people who pointed out I got my units wrong when we talked about the muons, I think that covers all of the, more or less all of the questions. Yes, but there is time now, an opportunity now for people to ask further questions. You can either ask them about what we've been hearing about, or you can ask more generally questions about what life is like in the physics department at Swansea. I see someone's just typed in, is there a space dilation as well as a time dilation? Yeah, the answer is when you do a complete treatment of special relativity, you'll find that it's not a dilation, it's actually a shrinking. So moving objects actually tend to shrink in the direction in which they're traveling, and that's called a Lorentz contraction. So one way of understanding Alice's, the fact that Alice felt that she got to Sirius in less than 9 years, was the fact that she knows that she's traveling at 8/10 of the speed of light, but she measures the distance to Sirius as being contracted. It's shorter than 9 light years, and so she gets there quicker. Again, we could have gone into that with not very much more complicated maths than what we should. It would have just taken more time. So while we're waiting, this is just a good opportunity to just remind you that there are further webinars tomorrow and on Thursday, and that we'll be covering other kind of topics we feel are exciting and interesting because they're because we like physics, and we hope that you do too. The other thing I can tell you about is that there is another, I have made another talk on the physics of dense matter. It's called How Dense Can You Get? That is publicly available on Swansea e-streaming site. We'll try and find a way to get a link onto the thing. In fact, we do have a web address with a lot of school resources. I'm not sure the best way for us to get this onto the screen. If I type it in the answer box, does that help? James, is that something? Can you? Hang on.
Yeah, I'll just pull it up. I mean, what we can certainly do is we should have email addresses for everybody who's registered, so we can do a mail shot and send out this information, both the links to your talks.
I think that's the best thing. If everybody's happy to get, do we have everybody's email address?
If you have not registered your email address and you would like this information, then please email me and I can be sure to send it to you.
Yeah, yeah.
I can answer a question, I guess, Simon? I'm not sure how to do that.
Okay. No, I don't know how to do it either. Someone's asked, what research projects have you worked on in your career as a physicist? So that's obviously something I'm delighted to answer. I'm a theoretical physicist, so I don't work in a laboratory. And my particular field of interest is particle physics theory. So particle physics deals with the elementary constituents of matter. And I'm also a computational physicist. So my research that I undertake is to use very, very powerful computers to explore the properties of subatomic particles called quarks. James, what's your research?
So by contrast with Simon, I'm an experimentalist. So my work is to do with the mechanical effect of light upon nanoscale motion. So what Simon didn't cover today, it's a little bit out of scope, is that light doesn't just carry energy, it also carries momentum. So when we know from Newton's laws that if something with momentum is deflected, then there has to be a recoil. So when light bounces off something very, very small, then that very, very small thing can change direction. Now, this is a well-known tool. It got a Nobel Prize not last year, year before. So it's used widely in laser tweezers, which is a technique from used in biology. This allows you to use light to not just look at microscopic things such as biological cells, but also to move them around. It's remarkable, actually, that you can do this with a biological sample without harming it. I don't use it for biology. Some of my colleagues do. But I use it for nanoparticles. So objects which are around 100 nanometers across. And we can, by using the control that we have through decades of engineering, improving lasers, we can use that control to try, well, there's various branches to my research, but one of them is trying to get these rather large objects into something where you have to use quantum mechanics to describe them. So it's really quantum mechanics from the top down, taking something which is definitely a lump of glass, a large macroscopic, so something that is close to our everyday experience. It really is a lump of glass, albeit a small one, and trying to make it behave in something like a quantum mechanical way. There's also, while I'm talking to you, there's also a question about year abroad on the physics course. So with my admissions tutor hat on, I'll say yes, there are year abroad courses. We have, these typically happen, well, these happen in the third year of a BSc course. So you'll do 2 years in Swansea studying the core physics, which is required learning according to the Institute of Physics and their accreditation. The third year can then be spent at a partner institution. It's unclear what will happen post-Brexit with this, but we are working carefully on this. I wish I could give more certainty on that particular question. This would be in 2 years' time for anybody starting now. After this third year, you then return to Swansea and complete the third year, the academic third year in your physical fourth year. So it does extend the duration of your degree by 1 year. It's worth it for many people for the extraordinary experience of studying abroad. And of course, you learn an awful lot more than you would do if you studied only for 3 years. We also have an arrangement with a university in Texas, not Texas A&M, Houston, whereby we have got a one-to-one correspondence between the first half of the third year. What you can do, and this is selected based on grades, it's reasonably competitive. We've had, I think, 3 people go through this now. You can study the first 2 years of your master's degree in Swansea, and then for the first semester of year 3, you can travel to Houston and study there. And then at the end of that, return to Swansea. This is cost neutral from a fees perspective. There's of course living expenses and some travel, but from a point of view of fees paid to the university, there's no change. And this does not extend your degree because you're studying the same material, albeit in a very different and life-enhancing and horizon-expanding environment in a very different culture. Back to my research hat, briefly, somebody asked, hence light sails, when I'm talking about the effect of light carrying momentum. Yes, indeed. This is exactly the effect that can be used to make light sails for propelling spacecraft. The momentum carried by light is extremely small. So the thrust that you get from a light sail is very, very low, but it can go on for a very, very long time. And the question is, another question is, would I recommend a year in industry in a physics degree or other STEM degree? So the year in industry, much like the year abroad, extends the duration of your degree by 1 year, and you gain an awful lot of experience. So we've had a number of people go through this. The way we run it is the onus is on the student to find a placement, but we assist with this, and we have some existing relationships. Once a placement is suggested, we go through due diligence to make sure that this is a worthwhile thing for you to do for a year. And some people find that this experience is enormously beneficial if they have a clear idea of what they want to do with their career. Since this does extend your degree by 1 year, it's not without, that there is that to consider. An alternative is summer placements. I highly recommend these. So lots of employers put on summer vacation placements. So these happen during the summer holidays. Therefore, they do not extend your degree. They're rather better paid than bar work or similar. And they, companies like these because they get to meet you. They get to see if you're a good fit for the organization. And it's a limited time thing. After 6 weeks, 8 weeks, or however long the placement is, then you go back to your degree and you both have each other's number if you decide you want to meet up again in the future. Okay, so there's a question about our degree schemes. Where's it gone? I think Simon has answered that one because it's disappeared from my screen.
Yeah, I answered one of them and probably
Okay.
I shouldn't have. I'll try and do the relativity ones.
Okay. Can light sail travel towards the sun, e.g. Venus? I don't know. That's an interesting one.
I think if you can sail against the wind in a yacht,
well, you have the
same
water
principle
to react against.
Oh, yeah.
So Simon is pointing out that you can sail against the wind in a yacht, in a boat, but you have a keel, you have a rudder. So
So you're in a medium. You're in a medium.
You're in a medium, indeed. I'm not too sure. I mean, there are lots of tricks you can play. For example, you could use it to slingshot around another planet. That would be a cheat way to do it. So for example, if you accelerated directly away from the sun and use the gravitational attraction of another planet to change your direction, you could do it. It would take you a very long time. I'm not sure if that's a satisfactory answer. That's an interesting question, though. I think the short answer is no, you cannot sail directly towards the light source using a light sail. But there are tricks because the solar system has other bodies which you can use to your advantage. Now, a question is, can you recommend some super curricular activities which would enhance a university application? So, in my role as admissions tutor, I do read personal statements. My overriding concern, or my overriding interest, is that somebody has the prerequisites and the motivation to study physics and thrive in a university environment. Things such as Duke of Edinburgh, I did it myself years ago, are fantastic. They're for personal growth and learning about who you are and what you want to do with your life. They're fantastic. They do, I suppose, help with demonstrating motivation, but I would rather you have 3 A's in maths, physics, and another related subject than essentially any other extracurricular activity that you might mention. I often see this is me speaking for Swansea University Physics Department. I cannot speak for other departments or other universities. But my concern is that somebody has demonstrated they can master the material and they are willing to put in the time to learn this difficult subject. They have the diligence and the commitment to do it. It's interesting if you've done unrelated extracurricular activities, martial arts, horse riding, whatever. These are interesting, but I'm not there to judge your worth as a person. I'm interested in your ability to study physics. Now, final light sail question. Could a light sail propelled by a laser carry a higher momentum? I'm not sure I understand that question.
It depends whether the laser is on the vessel or not. If it's on the vessel, then no. But if it's from if you're firing a laser at something, you can clearly make it go faster.
Oh yes, indeed. There's some excellent ideas for this. So one thing that's not quite light sails. So there is a proposed idea to use a sort of conical shape with a reflector on the bottom. You fire a laser up, and this focuses the laser light and ionizes the air. So this is clearly not a light sail anymore. This is using the energy rather than the momentum of the light, but it could accelerate something straight up into the sky. Once you've got something in space, then you can exploit the light pressure from the light carrying momentum, but you will come up against the Doppler shift. So as your vessel, shone on by a laser, accelerates further and further away, it's moving faster and faster. So the light it sees is now red shifted.
So therefore not as much momentum can be transferred.
I think that's the case.
Yeah. It boils down in the end just to conservation of momentum, and the point that James made, which is that light carries momentum as well as energy. And in fact, someone has asked a question about photons, and I think if you describe light in terms of photons rather than as a wave, they're both legitimate ways of thinking about light. In fact, they're complementary ways of thinking about light. But it's much easier to visualize a photon as carrying momentum. It is like a little bullet, but a bullet which doesn't have any mass.
That is a remarkable consequence of special relativity, actually. Yeah. That's how we understand that light can have momentum and yet no mass.
Yes, so if you're floating in space and you turned on a laser pointer, would it propel you? I think the answer is yes, it would. Wow.
Very, very slowly.
How many AA batteries would you need to get to Sirius? Someone's asking about other physics departments apart from Swansea. Are there any other physics departments? There are about 40. No, there are 30 or 40, and they're pretty good. Just about all UK physics degrees are accredited by the UK Institute of Physics. And you'll find that most physics degrees, roughly at least 2/3 of them will be more or less in common. Because physics is the same everywhere. It's a universal subject.
Yes, indeed. Oh, sorry.
No, it's just various departments have probably towards the third and fourth years of the courses, there will tend to be more courses, I would say, reflecting their particular research strengths. But the first two years, everyone does relativity, everyone does electromagnetism, everyone does thermodynamics, everyone does quantum mechanics.
So a related question is asking about a 4-year degree in particle physics and cosmology. So we have a variety of degrees, as Simon points out. These will cover the core physics for as required by the Institute of Physics, and then you can specialize. So in the fourth year, the second half of the third year, and in the start of the fourth year for a master's track degree, there's rather a lot of options available to you, and these reflect the interests of the department. Particle physics, the department, Simon won't point it out, he's part of this group, we really are world leading in particle physics research. This is the theoretical branch. We also have the ties to CERN, and that's, they make antimatter, and you can learn all about that on Thursday. So that is also unique and world leading. So if you want to learn particle physics, then a master's degree at Swansea is an extremely good option. I'm surprised that we don't have something that labels itself as a particle physics master's, but something approximating that very well is accessible to you through the optional modules which you can choose in the third and fourth year. Once you have your momentum due to light sails, what would be the plan for reversing this effect so you do not collide with another body? This is a real problem in space exploration. So if you manage to send a space probe by whatever means to a distant planet such as Pluto, by the time you get there, you're going so fast that you can't stop to make, if you want to get there in any reasonable length of time, you have to go to all the lengths you can to accelerate your spacecraft so that it's going so fast it will actually get there in a reasonable length of time. But then when it gets there, you've no realistic way to slow down. So no, we don't have a good way to do this. There's also something that takes.
I'm always worried about getting home. I mean, they've just got no sense of adventure.
Well, there's something called the Starshot program, which was an idea to send lots of very small satellites to distant, using light sails and other means to get them up to an appreciable fraction of the speed of light. But it suffers from this problem. Once they're there, you can't slow down. You could indeed just eject part of the ship, but then your ship would have to be rather a lot larger to accelerate in the first place. So it's a trade-off. It's an engineering question at this point. It's an interesting one, but we don't really have any good...
Actually, I think one of the real serious concerns is just if you bump into debris or dust or stuff, if you're traveling at these huge speeds, we don't really have a way of protecting ourselves. So you don't have to accelerate dramatically to get to very high speeds, but it's actually staying safe once you're there, I think is ooh. There's a question about home education there, James.
So the majority of, so the question is about people who are home educated. These, as you can expect, are in the minority of our applications. So we consider these on an individual basis. So A-level performance is a way to demonstrate your competence with the prerequisite material. It's not the only way. So if you have different circumstances, then we can discuss those. So am I keen on the film Interstellar? Yes, very much so. So, so somebody who was a consultant on that film, Kip Thorne, is a Nobel Prize winner, really instrumental in getting LIGO running, the gravitational wave observation. And he was a consultant on the film so that the ray tracers, the way in which they made these images of the black hole really were accurate. In fact, they had to tone them down a bit for the film, because in reality, if you were close enough to the main black hole featured in the film, Gargantua, then on one side, the accretion disk, so this is the dust, which is falling at an appreciable fraction of the speed of light, orbiting and falling into the black hole. And because it's falling, it's getting very hot. It emits light because it's hot. One side, it is traveling towards you very, very fast. And on the other side, it's traveling away from you very, very fast. So on one side, it would be blue shifted, and on the other side, it would be red shifted. But the producers thought this was too technical for the cinematic audience. So if you want to see what the renderings really look like, then they've published academic paper with all the gory details and pictures without this toning down. Yes, I like this film a lot. It's great to show how physics can be used to calculate things that we can't hope to observe directly, but we can really be pretty sure this is what the universe is like. We can calculate and we can predict. And most recently, we can test as well. Since the film came out, there's been, as close as we're likely to get, a direct observation of a black hole. I can't remember what the project was called. Let me see if I can find it while Simon answers other questions.
Oh, I know it's the book cover. Yeah, actually share the screen, put it on the screen.
Okay. Here we go. So this is the picture I was talking about. It's the Event Horizon Telescope. So this is a collaborative effort where using radio telescopes distributed across the world and some very clever, well, technology to make sure that we would all of these were taking the observations at the same time, and then some very clever software to combine these to make effectively one telescope the size of the Earth. They were able to reconstruct this image of a black hole at the center of a galaxy M87. I'm not quite sure how far away that is. So the shadow in the middle, which you can see, is the black hole, the event horizon of the black hole, from which no light is emitted. And the bright region you can see is an accretion disk. So light, dust falling into the black hole and getting so hot that it emits X-rays. You'll best come back tomorrow and ask Professor Kumar, to explain the details of how this image is formed. Because space-time is warped so significantly in the vicinity of a black hole, it's a little more subtle how this arises than what you might expect. So there's a question about multi-layer shielding used to protect space stations as a way to protect ourselves in a spacecraft traveling at some fraction of the speed of light. I think it's unlikely. As Simon emphasized at the very start of his talk, the speeds that we're talking about here are so so, I was going to say astronomically, but that doesn't capture it, so much higher than anything we've ever encountered for, well, except for the things made at CERN, but that's a very low mass.
Yeah, actually, that was a point I was just going to make, that it's traditional when talking about relativity to always talk about people flying around in spaceships, and it still does sound like science fiction, but actually effects like time dilation are real and need to be taken account of at particle physics accelerators. If the people running the Large Hadron Collider at CERN weren't on top of that, then they wouldn't be able to regularly accelerate the protons every time they go around, and the particles wouldn't get to the high energies that they do. So it does have, you know, real consequences which have to be taken into account.
And just for a order of magnitude, physicists like this order of magnitude answer, micrometeorites that might be encountered by a spacecraft in orbit will typically be going at about 10 or so kilometers per second. That's around 10,000 times slower than light. So we're talking about something going 10,000 times faster, and therefore having 100 million times more kinetic energy for something of the same size. So any technology we currently use to shield spacecraft would not be much help if we're talking about speeds around comparable to the speed of light. What advice would I give to students going to do physics at uni next year, end of September? With schools being closed. So next year I'm interpreting as 2021. I honestly don't know. It seems that there is talk of schools reopening. I don't know how wise that is. But I think if I were in this position, I would try my very best to read what I'm interested in and try to relax. Don't be too harsh on yourself given the current circumstances. You've still got until September 2021, more than a year. This lockdown now been going on for a month or so, two. There's a lot of time. So don't be too harsh on yourself. Read, remain interested, do some maths problems, but don't be too harsh if you find yourself not working as productively as you would like. A question for both of us, I think, Simon. At what age was your spark for physics ignited?
Ooh.
Yeah.
Well, for me, I answered partly to another. I actually find it quite difficult to decide between what I wanted to study. I was very good at maths, but I also liked all of the science subjects. And actually, I chose a university course which allowed me to pursue maths and physics and chemistry all at the same time. And then by the end of the first year of that course, I went for physics. But I'd actually find it hard to say why now. It just seemed like the right idea at the time, and I don't regret it.
I'm also a little vague on it. I can sort of go over old memories and with hindsight see that I always had an interest in this. One when I must have been about, I don't know, 6 or so, thinking about trying to understand why a puddle evaporated and concluding that there must be a thin layer on the top that was somehow very, very hot. Now, of course, we know that molecules in a liquid will have a distribution of speeds, and some of these have sufficient energy to overcome the surface tension and escape. But there's many little things. It's hard to analyze one's own motivations in retrospect because your memory is not a reliable witness. I also was good at maths. enjoyed applying this to understand the real world rather than just maths for its own sake. Yeah, enjoyed physics at school and decided I wanted to keep doing that. It was a bonus that there turned out to be quite a lot of careers accessible from a physics degree. I didn't study it because I was interested in the job prospects. I studied it because I loved it. And I guess that's why I've stayed in it as a career.
We're getting several questions coming in about what's going to happen this year as regards admissions and the university starting.
Okay, so we're awaiting UK and Welsh government decisions, but we're actively, so I asked exactly this question of our head of department and our director of studies. So people in the department have been extremely on the ball as all of this was happening. We're lucky to have some superb management in the department and the university. So I'll read out what they've said. Whilst we await UK government decisions regarding the end of lockdown, we are actively scenario planning within our department and the institution for the best approaches that keep our students and staff safe. Our current students will testify that we've adapted quickly and professionally to the pandemic, putting students as our priority concern. This will continue as we transition to the new academic year. We will adapt our programs where necessary to ensure social distancing, and we will use a range of processes to ensure students can engage as fully as possible with study and life at university. I wish I could be more clear. We anticipate that while life will be different and modifications to normal processes will be required, we can assure you that the physics department will continue to deliver a quality education and outstanding experience to all our students in a safe and supported environment. Now, some parts of that I'd like to emphasize just from myself. So we have students currently graduating, and you're planning to graduate this year, otherwise entering important assessments, and we have been managing these, I think, extremely well under the circumstances, with adaptations to the way we assess final exams, and managing to accelerate our delivery of course material in the lead up to the lockdown, so that we are in an excellent position when we did have to close the campus. Also, this is likely to, we're not just going to snap our fingers and go back to normal. This is going to be quite a long road, and we're, I'm optimistic that our management in the department have shown themselves that they are great at looking out for the best interest of students. I think they will continue to do so. There's lots going on behind the scenes trying to plan for all sorts of eventualities.
But the short answer is we are, as things stand, planning to start teaching again at the end of September in some form. In some form.
We're not quite sure how to manage this in lecture environments, which would typically have more people than will be sensible in one room. So we're looking at how we can adapt that.
I think we're coming to the end of today's session, and it's very much exceeded our expectations, I think, both in terms of the number of people who've shown up and also the engagement, the fantastic questions that you've showered us with, and in some cases the bad jokes as well. It's all appreciated. So I very much hope that all of you will be back again tomorrow to hear Prem Kumar talk about black holes and continue our journey into the wonders of relativity. Okay. So if anybody wants to get in touch, you can just you can drop me an email. You can find my email on the university website. My name is Simon Hands. That's Hands. Okay.
Just before you go, Simon, my name is James Bateman, and just failing all else, there's my email address on the screen.
Right. Oh, look at that.
If you want to contact me, then feel free to email me directly. Our colleague who organized the technical aspects of this event tells me that we should have all of your email addresses accessible. So I will send out links to Simon's other talks and a few other things that we talked about in an email to everyone, hopefully by the end of today.
That's brilliant. Okay.
Okay.
Thanks, everyone. We'll end it here.
Thank you. Bye.
Bye.